Happy New Year and welcome to the MIST102 series. So as we promised, I'm here to teach you some exciting and cool things in machine intelligence. I'm Hetal Pandya and this workshop is focused on convolutional neural network, a very popular type of neural network in the field of computer vision. In this workshop, we will be going over the representation of pictures in terms of pixels. We will then describe the components of a CNN, which includes kernels, stride length, padding, pooling layers, and dense layers. After understanding these concepts, we will use this knowledge to understand the CNN architecture. We will then dive deeper into data augmentation, which is a very crucial concept we would need to cover for the next part, the mini project. That's right! This workshop will help you build a 2D CNN personal project. If you have never made a CNN project, fasten your seatbelts as you're about to begin one. We then extend the concepts of 2D CNN to a 3D CNN and finally explore transfer learning and implement it in Python. Look at the picture to your right and try to analyze it for 3 seconds. What do you see? Buildings? Sky? Water? And probably you identify the CN tower too. You might be asking, why does this even matter? It's so trivial. However, the point I'm trying to make here is that we humans identify features in an image to decipher it. But this is not the case with machines. So this begs the question, how do machines see an image? And to answer this question, we will write a small Python script. The first step is to import the PIL and the NumPy libraries, which help us with image manipulation and numerical computation respectively. Next, we read the image from a local address and store it in a variable called image. We then transform the image as an array and store it in a variable called data. And then we finally print the image to uncover the way a machine interprets an image. Whoa, so what do we have here? A matrix of 3-dimensional vectors? And let me remind you that this mess of numbers represents the beauty of the city of Toronto. An image is divided into pixels. Each pixel contains information about the color of a section of the image. In our example, we saw that the dimension of the pixel matrix was 449, 612, 3. What does this signify? This signifies that the length of the image is 449 pixels, the breadth of the image is 612 pixels wide, and the depth is 3. Now what do we exactly mean by the depth? The picture that we just saw was in the RGB color scheme, which means that there is one channel each for red, green, and blue, making it 3 channels in total, and hence the depth is of 3. Remember that if we use any other color scheme, for example, if the image is in grayscale, then the depth is 1. So if a machine cannot see the features in an image, how can we make it understand the contents of the picture? The answer to this is kernels. So what is a kernel? A kernel is a matrix which is applied on the input matrix and it performs a dot product operation on the region it is applied to. In the picture to your right, you can see the yellow kernel with elements 101, 010, 101 being applied to the image matrix, and the resultant matrix is being filled to your right in red. These kernels are also called filters, and I'm sure that you have used filters before. However, the filters we will use here are not to beautify our images, but rather to extract local features from it. One important thing that you may have noticed is that applying a kernel reduces the dimension of the matrix, and the reduction of dimension follows the following formula, where n signifies the original dimension of the matrix and f is the dimension of the kernel. So let's implement a very popular filter called the Sobel filter. The matrix for the Sobel filter is stored in the variable called Sobel. We then create a new empty matrix using the dimensional formula we saw in the last slide. Because we are using a three-dimensional filter, the resultant matrix will be smaller by 2 units. Don't believe me? Try plugging in the values into the formula yourself. We then iterate through the image matrix, applying the dot product and storing the resultant value in the new matrix. As you see, this can be achieved using 2 while loops, one for rows and the other for columns. The Sobel filter is used for edge detection. Here is the output of the code we had written in the previous slide. As you can see, the edges of the building have been clearly extracted from the image. You can tweak the values of the kernel matrix and come up with exciting feature maps yourself. And to enable you to do that, I have added the link to the Colab notebook in the description below. So go ahead, pause the video and play with the code. A kernel is used for local feature extraction in images. To understand this, let's extract features from the below image. We will be applying the kernel on the left to extract the oblique lines in the image we have just seen. Kernels act on a local subregion of the image pixels and extract the features in that particular area. Therefore, the process of applying the kernel is also called local feature extraction. But how exactly does the kernel enable us to detect the oblique lines in this example? Can you see the symmetry along the red line? And notice the fact that the values on the line are marked positive, while the others are marked negative. Hence the emphasis is on those pixels that align with the diagonal. This should have given you a better idea of how these features are extracted. As we discussed, a kernel has 2 dimensions in a 2D CNN as it traverses along an image. However, very often images have multiple channels. For example, an RGB image has 3 channels, and hence the kernel must have a depth of 3 to traverse the image. Another example is a grayscale image, where the number of channels is 1, and hence a kernel has a depth of 1. I personally like to call this virtual depth, as depth of a kernel has a special meaning and it would be more clear as we study a 3D CNN. Stride is the number of pixel shifts over the input matrix. When the stride is 1, we move the filter 1 pixel at a time. When the stride is 2, we move the filter 2 pixels at a time, and so on. In other words, the number of pixels a kernel is shifted by when traversing the image matrix is called its stride length. You might also be able to see that if we increase the stride length, the dimension of the resultant matrix will decrease. The dimensionality of the resultant matrix follows the following rule. Here S is the stride length, F is the dimension of the kernel, and N is the original dimension of the image matrix. The image shrinks every time a convolution operation is performed. This places an upper limit to the number of times such an operation could be performed before the image reduces to nothing, thereby preventing us from building deeper neural networks. So how do we solve it? The answer to the question is padding. Padding is simply a process of adding layers of zeros to our input images. This prevents shrinking because if P is the number of layers of 0 added to the border of the image, then our previously n cross n dimensional image now becomes n plus 2p cross n plus 2p dimensional image after padding. The most common forms of padding are as follows. Valid padding. It means no padding at all, and it assumes that all the dimensions are valid so that the input image gets fully covered by a filter and the stride specified by you. Sane padding. It applies the padding to the input image so that the input image gets fully covered by the filter and the specified stride. It is also called same because for stride 1, the output would be same as the input. We have now covered all the concepts that make up a convolutional layer in a CNN. Now it's time to connect the dots. When we learned about the Sobel filter, we used fixed values for our kernel matrix. However, in a CNN, these values are learned by the model during the training phase. The layer that implements this operation is called the convolutional layer, and the output matrix is often referred to as a feature map. In Keras, the convolution layer can be implemented by the single line of Python code. Kernel size, strides, padding, and activation are few of the parameters that you can use in this layer. Keras also offers many other parameters that you can tweak to improve your model performance, and we are going to use some of them when we make a final project. Now let's cover another crucial layer of the CNN, the pooling layer. A pooling layer is a new layer added after the convolutional layer, specifically after a nonlinearity, for example the activation function ReLU. So after the nonlinearity has been applied to the feature map, a pooling layer is applied. Its function is to progressively reduce the spatial size of the representation to reduce the amount of parameters and the computation required in the neural network. Pooling layer operates on each feature map independently, and the most common types of pooling layers are average pooling, max pooling, and sum pooling. Average pooling. It takes the average of the elements in the feature map, and it can be implemented by the single line using the Keras in Python. As you can see in the picture below, what average pooling does is it basically sums all the elements and divides it by the number of elements and replaces the value in the resultant matrix. Max pooling. It takes the maximum of the elements in the feature map and replaces it in the resultant matrix. Again, it can also be implemented in Keras using the following line in Python code. Sum pooling. It takes the sum of the elements in the feature map. In the image below, you can see that all the elements are added together and replaced in the resultant matrix. Congratulations! We have now reached the final layer we need to learn in order to build a fully functional CNN architecture, the dense layer. To classify an image to different categories or labels, we need to flatten the feature maps to a single vector. Each value in the vector represents the probability that a certain feature belongs to a label. The fully connected part of the CNN network goes through its own backpropagation process to determine the most accurate weights. Each neuron receives weights that prioritize the most appropriate label. Finally, the neurons vote on each of the labels, and the winner of that vote is the classification decision. To implement the fully connected layer in a CNN, we can use the Keras code below in Python. The CNN architecture. So let's figure out how everything we learned so far connects together. The image is first processed by blocks of convolutional and pooling layers. It is very important to note that when we add more number of convolutional layers along with pooling layers, the depth of the model increases. As a matter of fact, you can observe that if we increase the number of layers, we will be increasing the number of variables we need to train whilst decreasing the dimension of the feature map. The next and the last step is to flatten the feature maps into vectors for classification. After learning about the CNN architecture, you may ask yourself, which architecture is the best? The answer to this question is a matter of ongoing research and depends a lot on the dataset you are training your model on. However, there are a few architectures that emerge from numerous research papers which are popularly used for various tasks. We will explore one such architecture in great detail when we talk about transfer learning.